Good afternoon everyone, and welcome back to my worked exam answer series. I'm really sorry that I've been somewhat absent from TikTok and YouTube recently, but I'm hoping that I can be back in some capacity between now and the exams, because it's so important for me to be able to help as many of you as possible with your upcoming chemistry GCSEs, AS exams, and of course the A-level exams as well. So please do let me know if there's any specific sorts of questions that you would like me to tackle. I've got a few in the pipeline, but after that I am very much open for suggestions. So please do let me know if there's anything specific you want me to have a look at. Today, off the back of a poll I did on Instagram, I'm having a look at an A-level question, and I've chosen this one on esters because there's quite a lot of application in this question that relies on you knowing about esters but maybe seeing things in a different way, or being asked questions about things that relate to other areas of organic chemistry that we need to bring in to this particular question. And something that's been a bit more common of late is them giving you a mechanism that you're not familiar with. So this isn't a mechanism that you need to know, but you have to use your knowledge of mechanisms more generally to be able to add the curly arrows that we're going to need to add to complete this mechanism. So we'll work from the top as always, and at the end, if anyone's got any questions, as always again, please just let me know. So we're thinking about esters, and more specifically the diagram shows an incomplete mechanism for the reaction of an ester with aqueous sodium hydroxide, and we can see here what those steps look like. So we've got our ester, then we're using an OH minus ion, and the products at the end of step 3, we've got an alcohol and we've got a carboxylic acid ion, the carboxylate ion, as opposed to the carboxylic acid itself. And the first thing we have to do is add 3 curly arrows to complete the mechanism in the above diagram. So when it comes to knowing where these curly arrows should go, if this isn't a mechanism that is one you have to rote learn, how are we going to be able to do this? Well, we've got the products of each of the steps. So we can see, for example, step 1, we've got this OH, which is, I would suggest, acting as a nucleophile. It's using its pair of electrons to attack the C of the C double bond O. And if we then compare that to what we've got at the end of step 1, we can see the C double bond O is not there anymore, and has become a C single bond O. So that would suggest that in this step we need to break open the C double bond O. Also, this is what happens when we do either nucleophilic addition, or it's the first step in nucleophilic addition elimination as well, where the nucleophile attacks the carbon, which means that this OH is then going to add to this carbon, and we can't therefore not break one of the existing bonds, because otherwise carbon will be forming 5 bonds. So our first curly arrow is going to be from the CO double bond to the O. And like I say, I know it's going to be that one, because if we then look at the product of step 1, we can see the CH3 is still on there, the OCH3 is still on there, the OH nucleophile is now on there, and then we've got the C single bond O here. In terms of how I knew this OH was acting as a nucleophile, it's got a lone pair of electrons, which it is then donating to this carbon. So again, it's helpful to know definitions for nucleophile, electrophile, base, from an organic point of view certainly, and also to have a bit of an idea as to what we mean by substitution and addition and elimination. So that's our first arrow. And then we can see we've got this intermediate at the end of step 1, and they've added 1 curly arrow to show how the C to O double bond is then going to be reformed, which we can see at the end of step 2 has been reformed. And then we can have a think about what is no longer present. We've got the CH3 still on there. We've got the C double bond O, which accounts for this curly arrow between the C and the O, well, the lone pair on the O and the bond here. And the bit that's now not there, because the OH is still there, is the O to CH3. So again, this is kind of similar to nucleophilic addition elimination in that we've got the double bond reforming, and it's that reformation of that bond that then enables us to eliminate, in this case, the OCH3. So we're going to go from the carbon-oxygen bond to the oxygen like that for our second curly arrow. And that means that this CO bond will break and this oxygen will leave with both of those electrons. And as we can see, that's what we've then got here in this OCH3, where the O has a negative charge because it gained back its own electron and the electron from the carbon. And we can see that that's now attacking a H. And again, we can then look at what then must happen in order to give us the alcohol, CH3OH, which is going to come from the CH3O and this H that O is attacking. And then we've got the CH3 C double bond O minus. So we need to separate the O and the H here, and it's the O that needs to have the electrons. And again, I know that because the O is negative. So from the OH bond to the O will be our third curly arrow like that. You wouldn't have to name that as a mechanism, but like I said, it is very similar in the first two steps, certainly to nucleophilic addition elimination. But then we've got this additional step on the end here, but we are going to need to think about the type of reaction that's shown in the above diagram. So there's a couple of ways that we can think about this. We can either use our knowledge of esters and the reactions of esters to recognise that esters can be hydrolyzed in the presence of either an acid or an alkali, like we've got here, the sodium hydroxide. Or we can also, again, just have a look at the mechanism and be aware of what different reaction names and types are referring to. So hydrolysis is splitting up of a compound using water. We've got the aqueous component here, and we can see that this initial ester is now two separate things at the end. So we've split it there between the C double bond O and the C single bond O. So we're going to go with hydrolysis. And whilst I don't think you would need to specify that it's alkaline hydrolysis, again, we know that it is because we've got sodium hydroxide being used, but also we can tell it's alkaline hydrolysis because we don't have the carboxylic acid being reformed. This would be our carboxylic acid salt. So type of reaction is going to be hydrolysis, and I'm just going to put in brackets that it would be alkaline hydrolysis, and that's something that may be helpful in the final question of this, or the final part of this question. Okay, now we've got to deduce the role of the CH3O minus ion in step 3. Now the word role probably feels a bit out of place in a chemistry exam, but as I believe I've talked about before, when we're thinking about roles from an organic point of view, which we are here, the sort of answer it's going to want you to give, nucleophile, electrophile, base, possibly a catalyst. In other contexts you would also have acid, oxidizing agent and reducing agent to consider as well. But here, again, in terms of how we know this, it's a deduce question, so we're not expected to know, we're expected to be able to work it out from the mechanism. So what is this CH3O minus doing? Well, it's using its lone pair, but it's not acting as a nucleophile. It's not donating a pair of electrons and attacking something that is partially positive, as was the case here. It's using these pair of electrons to accept this proton. So it's therefore acting as a base, because a base is a proton acceptor. And again, we've seen this kind of role in elimination, one of our year 12 mechanisms, where the OH takes the proton from a neighbouring carbon to where the halogen is, and that OH minus is then acting as a base. So that's what's going on here. And again, if we understand how mechanisms work more generally, we'll be able to figure that out, even though this is a mechanism we've never seen before. And then finally, we've got a triester, which is exactly the same as an ester, but we've just got 3 ester groups in there. So a triester exists when we use glycerol as our alcohol, glycerol being propane 1,2,3 triol. So we then have 3 OH groups in the same molecule, which we can then use to form 3 ester linkages in the same molecule. And these triesters can react with sodium hydroxide in a similar way. So we're still thinking about alkaline hydrolysis, but when we think about doing this with a triester, we are specifically thinking about saponification, which isn't any different to alkaline hydrolysis. It's just a more specific term when we're thinking about triesters. I think it's also potentially helpful at then thinking about what we have to answer here, which is to give a use for the product of this reaction. And this is where also recognising that we're doing alkaline hydrolysis and we have the salt of the carboxylic acid being formed rather than the carboxylic acid itself is important, because the salts of the carboxylic acids that we make from these triesters can be used as soaps. And that would not be the case if we were to use an acid for the hydrolysis of the ester, because we would make the carboxylic acid rather than the salt of the carboxylic acid. So there we go. Hopefully I've explained that in sufficient detail for everyone, but if anybody has any questions, anything they'd like to clarify, or have any questions that they want me to work through that they've struggled with, please just get in touch. You can leave a comment on the video, or you can DM me or send me an email. I'm sure you know where to find all of that information by now. And thank you so much for sticking with me, and hopefully I can get lots more videos out between now and your exams. I hope that your revision's been going well, guys, and again, if I can help with anything, please do not hesitate to ask. Thank you so much for watching.